Alright, hi y'all. Today we're going to be going over a microprocessor's stack pointers. So really just the push and pop types of, functions, I guess. So the first thing we have to know is, for this topic especially, what is a stack pointer? Well, stack pointer, especially in assembly code, will point to the address of either the top element or the bottom element, depending on whether you do the push or pop. Now, how do we know whether, it's the top element or the bottom element? Well, before we get into that, we need to know what a stack looks like and how it's arranged. If you already know this, you can skip ahead, but this is for people that are getting into this. That way, what I'm doing doesn't make it and literally no sense at all. So let's say we have the computer here and it's storing memory. And we want to, design it. It kind of just looks like this box here. We can have this box here. Now, this is the memory that, the computer will store, data in. Now, what exactly are these boxes for? They have these boxes. How much do they take? Or how much can you put in here? Well, each box is 4 bytes. Keep this in mind. It's very important for memory allocation and figuring out which memory address you're allocating for this data. So when you have these, each of these are 4 bytes, we want to put in something into this memory, or it's called a stack. We want to put something into the stack. Now, the way we do this is we use the function called pop, or not pop, push, sorry. Push will put things into the stack. Now, let's say we want to put R1, R7, and R6. You're going to put these registers into the push, or into the stack, pushing them into the stack. The way you do this is you take your least number, okay, the smallest register number. It goes on the top. So, for example, R1, R7, and R6. Which one is the smallest? Not the smallest value, not what is inside the register. Whatever register comes first in the numerical order. So if it was 1, let's say you had 1, 0, and 2. Well, 0 would come first, so it would go at the very top. It doesn't matter what order you put them in. It could have been 6, 7, 1. 6 doesn't go first. 1 goes first. 1 goes on the top. Following this, logic, which should go second, which register should go second? Well, it should be R6. R6 should be second because it's the next smallest. Then, of course, you have R7. Each of these boxes, again, holds 4 bytes. So each of these are going to be ending up inside of these 4 byte, kind of confinement squares. And this is how you put them into the stack. Now, if we want to, point to this stack, especially in C, whenever you use a lot of pointers, you have to point to the top of the stack. Whenever you push, the memory address put into the SP register, which is register 13, it's a special register called the stack pointer. This will always give you, not always, but whenever you push something into it, it will give you the memory address of the top element when you push. Okay, so if you were to go into Keil or whatever, assembly language, or not language, but compiler you have, if you were to play around with this and put this code in here, you would see that register 13, the stack pointer, will change when you have a push or a pop. Now, hopefully y'all can understand so far what's happening. So let's say we want to, now that we have this in the stack, this is the stack here, we want to take out something, okay? So let's say now we want to take out R1 and R6 and put them into registers R2 and R3. Or you want to take out just register 1, okay? you'll do is you'll say pop, you want to take out R1 and you want to put it into R2, you would say R2. Okay, so what this will do, I'll do one register so you can see how this works, and then I'll do more so you can see the complexity of this. So now what you do is you make a new box. This is the way I do this. It makes a little more sense for me. What I do is I put R2 here, and you put an arrow to the register that it is taking it from. This, you always put it to the top register. The very top register will get taken out first. Okay? So what this means is whatever's on the top will get taken out first, and it will be now put into R2. So now R2 is equal to R1 instead of R2 being whatever it was before. It'll make more sense whenever I put more elements into this. Let's do pop R2, R3, and R4. So now, just like we've done before, which one will go first? Well, R2 will go first. Then R3 will go second, and then R4, because you're going from least register number to highest register number. Now you put your arrows. R2 goes to the top element. The second element of your pop will go to the second element in the stack, and your third element of your pop will go into the third element of the stack. Now what you can say is R2 is equal to R1, R3 is equal to R6, and R4 is equal to R7. So what you've done is you've changed your register values using the stack. You've used push and pop to change register values. Now, what if we didn't use all three? What if we only have two here at the pop? What does that do? Well, 4 won't be here anymore, so we don't have this arrow here. And R2 will still be equal to R1. R3 will still be equal to R6, but R7 is left in the stack. So now we'll redraw the stack after pop. The stack will then be R7 by itself. And if you push something into this, so now let's say we were going to go into another set of code. We have our new stack, and our stack has R7 by itself left. It's going to stay at the bottom. For example, if we push R0, R1, and even if we put R9, okay, we act as if this isn't here. That stays at the bottom. It will not change its position. So what will the new stack look like? Well, this new stack will look like this. We put R0 first, of course, R1 second, and R9 goes here. It does not go at the very bottom. R7 has to stay there. So now, if we do again another pop, we do a pop of said, let's say we did pop, I don't know, R2, R3, R7. What happens now? Well, we draw our new, just some placeholder. We put R2, whatever is in the pop command, R3 and R7. And now what happens? Well, R2 corresponds to the top element of our stack, R3 corresponds to the second element, and R7 corresponds to this element. So what can we say? R2 is equal to R0, R3 is equal to R1, and R7 is equal to R9. Notice how this R7 stays in the stack. That is your old value of R7. This new value of R7 will overwrite the old value. It'll make more sense when we get into this practice example, but this is kind of how we're going to be doing this. So this is how you get new register values. So this is for new R values, new register values. This is how we use push and pop. But what about the memory address? I kind of went on about, 4 bytes of each one. How does that even play into this, right? What happens here is whenever we push or pop, you have to add or subtract that number of bytes in hex. So let's say, for example, this is for memory address. Let's say we have our initial starting, I forget, stack pointer. Let's say stack pointer not, the initial is 0 hex 200000400. Okay, and we want to push 4 different registers, so R0, R1, R2, and R3. Whenever you push, you are essentially pushing the stack pointer upwards, because remember, the stack pointer will point, so I'll put a note here, when stack is pushed, stack pointer decreases. When stack is pop, the stack pointer increases. Now, how many bits or hex values does it increase or decrease by? Well, this is what I'll show y'all here. It's very, very easy. This is very easy, equation you can use. So let's say after your first stack, right, your initial stack, then you go to a different stack, so you have another stack pointer. Your stack pointer 1 will be equal to stack pointer 0, your initial, and if it's push, you decrease, so it'll subtract 4 times the number of registers. So in our case here, what we're going to do is 0x200000400 minus 4 bytes times how many registers? 4. So this is 16 bytes, or 0x1, 2, 3, 4, 5, 6, 7, 8 in hex. So hex will be this number in bytes. 16 bytes is this in hex. So then SP1 is equal to 0x20000, and now we have 3F0, I believe, right? Because we take away 1, we get 15 instead of 16, and we have to borrow from the 4. So that's our new stack pointer. But what if we popped? Okay, what about pop? Okay, and let's say this is in sequence, right? We've just done our push, and now we want to pop something out of the stack. Okay, well, that means we have a stack pointer 2. This is how I keep track of it. I usually use subscripts like this. So now what we do is we do stack pointer 2 is equal to stack pointer 1, because we just did a push, so now our initial stack pointer is stack pointer 1, and we do pop, which is a plus. Again, 4 times number of registers. Now, number of registers is not the total number of registers, of course. This is the number of registers in your command. So if you did, let's say pop only R1. If we only did R1, then this is 1 register. Okay, let's say we want to do pop R0, R1, R7, R6, R5, and R4. Well, this is what? 6 registers. So you would multiply 4 by 6 and get 24. Then you would change that into hex, and then you add. This is how you do this. That's how you find the new stack pointer. That's the memory address. Very, very simple. So now that we've done this and we've gone through the, sort of basics, let's go to an actual example given here. I'll copy this and I'll paste it further down. Okay, so let's go here and let's paste this and let's try this out. This is similar to what Dr. Lay did in class, but I added some stuff just to make it a little harder because, you know, all of the registers went away at the end. I want to make sure we know what happens when you keep them. And I also added some stuff in between, subtraction, some adds. You could definitely do some multiplication and unsigned division here too, so be careful of that. You also have to know when those registers in between the pushes and pops don't matter. And you'll see what happens here. So looking at this, we have, you know, this is just our basic move. So we're moving those values into the registers, you know, initializing our register values. Okay, that's very easy. Now, we are subtracting R5 and R2. So how do we read this? We go from right to left, or I guess it's just an equation straight away. So it's R3 is equal to R5 minus R2 is equal to what? 0x15 minus 0x12 is equal to 0x03. So that's our new value of register 3. Very simple. We will use this. Now, we have this pop. Okay, let's draw our stack. So something I like doing is labeling each of our pushes and pops. So this is our number 1, this is 2, this is 3, this is 4, and this is 5 here. So we have 5 separate occasions where you either push or pop. Okay, so let's say at 1, what do? Well, we're pushing stuff into the stack. Okay, well, it's R5, R3, R1, and R2. How do we, you know, put this into the stack? Well, remember, the least number register goes on top. R5 does not go first. R3 does not go first. R1 will go first. And it doesn't matter, by the way. I put these in order from least to greatest, 10 to 16. It could be the other way around. R1 would still go first. It does not matter the value inside the register. It is just the register number. I guess I should have put, you know, different numbers. Maybe he'll do that in the exam. Just be careful about that. So what we're going to do is 0x, what is R1? 11, right? Now we do R2. Well, R2 is equal to 0x12. Then we have R3 is equal to 0x13. And R5 is equal to, R5 is 0x15. Does that seem right? Right, we just took the values from here and we plugged them into the stack. That makes sense, right? But be very careful. Remember, the very first thing we did was we subtracted and replaced R3. That initial R3 is not our R3 value anymore. We're using OX03. So R3 must be this now. OX03. That's something you guys have to be very careful of. And we're pushing, so this is a push. Okay. Now, by the way, I'm going to do only register values first, and then second, I'm going to go back and find all the memory addresses. So if you're only here to find out how to get the memory addresses, go towards the end of the video. I'll be going through them. The first half is going to be more of this push and pop register value stuff. Okay, so now we've gotten push. The next thing, straight away, we go into the second push. Okay, well, let's go. We label this 2. We call it a push. So we're adding things to this stack. So you know what? This is going to be a little longer, so let's make it a little bigger. Okay, now what do? Well, let's look at the values of the register, not the values, the register numbers of the second push. Well, the second push has, you know, 0, 1, 2, and 3, right? The first one, R0. R0 is still its initial value, 0x10. Then it goes R1 is equal to 0x11. Okay, R2 is equal to 0x12. Okay, but wait a minute. We have 2 R1s. Shouldn't R1s stick together? Shouldn't we put R1 is equal to 0x11 and then R1 also here? Because, 1 is less than 2. That's a very common misconception when dealing with these kinds of things. But remember what I'd said before. Whatever is in the stack earlier does not switch spots. It will stay at the bottom. So what you're going to do whenever you have the exam and they, end up doing this, which I'm pretty sure he will, because we have to draw out these stack kind of images, he's going to put something where that not all of the register values inside of your stack gets popped. Some of them will stay. What you have to do is you leave that at the very bottom, no matter what. Leave it at the bottom, and it'll be the last thing to come out of the pop. Okay. Now we have R2. What comes after R2? R3 is still in the second push. What was R3? R3 is not 0x13. It is 0x03. Now you put all of whatever was in here at the very bottom of your stack. Okay, so we have R1, and you put it in the same order, by the way. You don't change the order. Definitely don't do that. 0x03, and R5 is equal to 0x15. Perfect. So we have all of our second push done. All right, what's next? Well, we have a subtraction. What we have now, R3 is equal to R1 minus R0. What was R1? Well, R1 hasn't changed, so we will keep it as 0x11 minus R0. R0 has not changed either, so it would stay as 0x10, and this is equal to 0x01. So that's our new R3 value. This will be the new R3 value. I'll show y'all why that might not matter so much. Okay, but okay, now we go on to the next step. We add. Okay, well, we read from left to right here. R4 is equal to R1 plus R4. What is R1? Well, R1 hasn't changed. Definitely not. R1 is 0x11. Plus, we add R4. What is R4? Well, R4, has R4 changed? No, we haven't popped it out of the stack. We haven't, done some other arithmetic before. So R4 will be, well, it'll stay the same, right? So 0x14. So this is 0x25. All right, now we go on to step 3, which is another, not a push, but a pop now. Finally, we've gotten to a pop. So now what we can do is 3. This is a pop. Okay, so what are we doing here? Well, let's draw this kind of dummy stack. It's not an actual stack. It's just a dummy stack for you to understand how things go from one to the other. Now, what does this dummy stack have? Well, it pops R1, R2, and R3. The exact same as the push. Whenever you do your stack and you're doing pop, you rewrite R1 goes first, R2 goes second, and R3, regardless of the values. Note, R3 is now 0x01. It's the very smallest it can get, besides it would be 0. It's not going to go first. It goes at the very bottom because it's third resistor. Oh my god, third register. Now what we're going to do is we're going to draw arrows to the corresponding registers. The very top element of our pop, man, what do they call it? Oh my god, the pop stack corresponds to the first element of the push stack. And now we do this and this. I'm definitely using wrong terminology. I'm just trying to make it easier for y'all to visualize. But now what you can say is R1 is equal to, well, the value inside of the push stack, 0x10. R2, 0x11, and R3, 0x12. Notice what is left. Well, what's left is, so we'll write this is stack after the step 3. This is the pop. The stack that's left over is this. Everything will get shifted up. It'll be 0x03, which is register 3. The old register 3, remember. Then you have 0x11, 0x12, 0x03 again, and now we have 0x15. Okay, so this is our stack after the third step. Let's rewrite all of our, all of our register values just to make sure we're kind of holding on to what's happening. So we have R1 through R3. What happened to this R3 though? Didn't we just subtract and we got this old R3 value? I mean, why are we just, rewriting it? Well, that's what happens. When we pop something out of the stack, it will overwrite whatever was previously stated. That's why I said on that step for the subtraction, it's a new value, yes. And that's what will show up in your register values for your compiler, but you won't ever use it. The new R3 value is actually 0x12, hex value 12. Now, what's the new value for R4? Well, nothing came out of the stack, so whatever we added here is R4, 0x25. What about R5? That's still in the stack. It's still here at the bottom. That means it has not been overwritten, and it will be the original value. So R5 will still be 0x15, hex 15 here. What about R6? Has R6 been overwritten? Well, it doesn't look like it. R6 is still 0x16. So these are our register values so far after step 3. Okay, now let's look at step 4, or what happens after, the pop of 3. Well, we have to add. Okay, so now R5, right? We're doing R5, we're adding R1 and R2. What is R1? Our new R1. We do not want to look at the old one. The ones that we've just written, R1 is 0x10 plus R2, hex 11, 0x11. This is equal to hex 21. So R5, now what we have to do is we rewrite. This takes its spot right after we've just, taken out of the stack. We've just written all of our values, and wow, we get an addition, R5, R1 plus R2, that's our new value. Okay. Now, we have to push. Step 4. We push. Okay, so we have another push. That means we're adding to the stack. So that means we have to, add again R0, R6, R4, and R5. Okay, just like we've done before. R0. What is R0? R0 is equal to... Oh, that's what I forgot. R0 here. What the heck? R0 hasn't changed, right? Nah, we're good. 0x10, it looks like. Staying the same, R0 hasn't changed, so we're just letting this be 0x10, x10 here. Okay, now we're putting in, what is the next value? The next least, register number, R4. Well, R4 from our new values is 0x1025, sorry. I don't know if you can hear that in the living room. Now we have R5 and R6. Remember, you want to do in ascending order. R5, we use the new R5 value we got. If you use the old one, you'd be wrong. 0x21 is next here. And R6, 0x16. And now, well, that's not the entire stack. We have to take what we found to be the stack after the third step and put it into the fourth step at the very bottom. So now we have 0x03. This is going to get a little cramped, I think. 0x11, it's fine. 0x12, 0x03, and 0x15. Okay, cool. So we have our stack after step 4, and now we look at the next line of code. It says 5 is pop. It's the last step. Okay, nice. So we'll come over here, we'll write this. We're writing a pop. And what values? Well, gee golly, that's all the fucking values, huh? Sorry. That's 0 through 6. Okay. So what we're going to draw is we're going to draw a new dummy stack. R0, R1, R2, R3. Sorry if y'all can't see if you want to see the code here. Actually, I need to write. Sorry. R4, R5, and R6. So looking at all the new values, all the values will be changed. Unless, of course, they don't, which in the first one they don't, it looks like, right? So we have R0 goes to the top element. So what R0 is going to be equal to R0, which is 0, 10, hex 10. Then we do the next one, R1 will be equal to hex 25. Remember, you can see we're going from right to left, which is kind of a theme for assembly. Kind of weird, in my opinion. Then we do this. R2 is equal to hex 21. R3 is equal to hex 16. R4 is equal to hex 3. R5 is equal to hex 11. And R6 is equal to, again, hex 12. All right. So these are our register values, our final register values. And just so we can check ourselves here, we're going to make sure that we got the right register values. Hopefully it doesn't go too slow. Go here, make sure this is the same code. It seems to be. Hopefully y'all can see the entire screen. We're just going to go to the very bottom and check our values. So I'll build, make sure the values, no errors, whatever. And we will run this. Go to the very bottom. And we will check ourselves. So we have 10, 25, 21, 16, 3, 11, and 12. Perfect. That's how we check. You know, make sure to check yourself whenever you're doing these types of problems. These are very easy to check. Plug it into your assembly, and you just solve for you run it, find your register value. So we got it right. Now what we have to do is we have to do our what's it called? Oh my gosh. I totally forgot. Oh my gosh. Actually brain dead right now. Our memory address, sorry. So the only thing that affects memory addresses is our push and our pops. So for pushes, remember the equation above. We have the starting register SP0, or we'll say SP1 is equal to SP0. For pushes, we do minus 4 times the number of registers. Okay, well, let's say in our case, because this is the same thing for my assembly here, SP0 is equal to hex value 20000. Is it 400? I believe, yeah. So that's going to be our SP0. So SP1 is equal to this hex 1234400 minus 4 times the first number of registers, which is, here, 4 registers, 1, 2, 3, and 5. So 4 times 4 is 16, which is equal to 0, the hex value 0, 0, 0, 0, 0, it's 5, 6, 1, 0. This is 16. So now SP1 is equal to hex value 2, 1, 2, 3, 4, 3F0. That's going to be our first, SP1. Now, SP2, and you'll notice the reason I put these 1s and 2s and 3s is because they match up with these 1, 2, 3, 4, and 5 at the very left. That's kind of why I do it, just to make sure everything, stays right. What we notice here is we have SP2. The second step was a push. It's the exact same thing. So what we're going to do is SP1 minus 4 times the number of registers is equal to hex value to 1, 2, 3, 4, 3F0 minus the 4 times the number of registers. Now, we're not looking total. We're looking at the number of registers done in the command. And it looks at, it's be 0, 1, 2, and 3, 4 registers. So you do 4 times 4, again, 16 bytes. Forgive me. Yeah. So then, again, this is the exact same one here. So then we do SP2 is equal to hex value 2000003E0. The way I'm doing this, by the way, if you aren't seeing how I'm just taking away and I'm solving these kind of quickly, we know F to E is minus 16 bytes. Or hex, in hex, it would be minus, this value here. In hex, you're in base 16. So if you have 16 bytes, you can take away just one entire, base 16 of the second position in hex. So now SP3, what happens in the third step? Well, SP3, let's look at the third step. Let's look for number 3. There we go, 3, a pop. So now instead of subtracting, we're adding. SP3 is equal to SP2 plus how many registers? Well, look right here. 1, 2, 3. So we have 3 times 4, right? Number of registers 3, 4 bytes per. And we get 12, right? So 12 can be rewritten as hex value C. You don't have to put all these zeros. You could literally just put this if you want, hex C. So now SP3 is going to be equal to hex value 2, 1, 2, 3, 4, 3E0 minus hex value C. If I remember correctly, this can become a D, this becomes an F, F minus C. Well, not really F minus C, it's like 16 minus C, right? So this would be 16. 16 minus 12 is 4, D minus 0 is D, and this is 3D4. So 0x 2, 1, 2, 3, 4. That should be right. I'm probably wrong. We can check ourselves though. The way to check yourself, oops, that's the wrong thing. Good thing there wasn't anything on there. I mean, shouldn't be. We can check ourselves real quick with our code here. So we can do the same thing as we've done before. We can check our 13th register, and we are on step 3, which is the first pop. Okay, 3EC. Okay, yeah, I figured I did something wrong. Oh, we're adding. What am I doing? Subtracting, right? Yeah, y'all are probably thinking I'm a fucking retard. That's crazy. Anyways, we're doing plus, so we're not doing any subtracting. I don't know what I was doing. So 3EC, perfect, right? 3EC. I even wrote it right here. I don't know what I'm doing. All right. So this is our, and we just saw 3EC, perfect. Now SP4 is equal to SP3 plus or minus, depending on push or pop. Let's check the fourth step. Fourth step is a push. So it's minus 4 times. Let's look at how many register values are in step 4. It looks to be 4 again. Okay, well, lucky me, it's 16. All right, so this is 16. So SP4 is equal to hex 2, 1, 2, 3, 4, 3EC minus, I guess 0 hex 1, 2, 3, 4. That's a 0 here. 0, 1, 0. And we take away an entire E. So that becomes a D, right? SP4 is equal to hex value 2, 1, 2, 3, 4 zeros, 3 DC. And SP